Hi, and welcome to today's webinar on model-based definition. At the onset of engineering information, before there were computers and computer-aided design, drawings were used to completely define a design's specifications. For many years, their significance was due, in large part, to the role they played historically, and then came CAD. At first, 2D CAD programs were used to speed up the process of drawing creation. In addition, these programs also made it easier to make design changes and improve engineering workflows. Even when 3D CAD was introduced with its own improved workflows and added benefits, 2D drawings were still the main conveyor of a design into a manufacturing setting. For most of the existence of modern design, 2D drawings have been essential. As 3D CAD evolved, a shift to the engineering design approach ensued, where engineers would design the 3D model first, followed by the semi-automatic creation of the associated 2D drawing. This allowed engineers to spend less time refining the 2D detailed drawing. As a result of these added benefits, 3D CAD became the mainstream design tool of choice. Even with this evolution, companies still had redundancy in information, all because of the collaboration aspect of sharing information. While engineers could design in 3D, many of the consumers of that information for downstream applications were still relying on the drawing. The thing to think about, though, is that if the 3D model is the source of the information, the single truth, then 2D views of it are only interpretations. Even one misinterpretation can cause severe problems. The existence of redundant data required to define a manufactured part can lead to several issues. First, it prolongs the product development cycle. The time it takes to create a detailed drawing is often greater than the time it takes to create the 3D model. When you add up the time it takes to create both the model and drawing, and also add in other variables like searching, opening, editing, and verifying this redundant information, that's added time to getting the product out the door. Secondly, manufacturing drawings can often be difficult to read. Interpretation errors, duplication errors, or revision inconsistencies can contribute to costly mistakes. With pressures to get a late project out to manufacturing as quickly as possible, it's often easier to just change the drawing and override a critical dimension, leaving the model out of date. The use of 2D drawings for the purpose of communicating downstream production requirements adds an unnecessary burden to the product development cycle. A simple change in the product definition not only requires updated 3D digital data, but also necessitates numerous engineering changes to all 2D documentation associated with the product. Since it takes time to maintain this documentation, the life cycle for implementing a product change grows with the extent of its associated 2D data. Over the next 30 minutes or so, we want to introduce you to some of the challenges facing many companies today as it relates to capturing and disseminating engineering information. To address these challenges, we'll show you how technology built inside of the Solid Edge portfolio of products allows for engineers and designers to easily capture their information during the design process and quickly push that information downstream without the need for creating redundant information. This product manufacturing information can be easily leveraged from within the natively designed Solid Edge data or from data coming from outside modeling sources. We'll show how all of this information can be encompassed in easily readable model views and then pushed out to non-CAD consumers in widely used formats such as 3D PDF or HTML so that everyone has easy access to the data they need. One of the keys to eliminating redundant engineering information is to capture and retain it through the use of model-based definition. Since product teams can capture and share the engineering requirements, such as geometric dimensioning and tolerancing, materials, and assembly level bill of materials within the 3D model, the need for creating the 2D drawings is eliminated and it ensures that the final product complies with its engineering specifications. Let's take a closer look at how Solid Edge incorporates product manufacturing information. The execution of applying PMI to Solid Edge models is relatively seamless. Here are just a few examples of capturing important product information on both a single component as well as at the assembly level. Besides consuming this information within the CAD software itself, This information can also be conveyed to and read by Solid Edge manufacturing software, ensuring the parts are manufactured to the correct specifications. Other options to export PMI with the CAD model include JT and STEP AP242. In a few moments, we will demonstrate some ways that this information can be captured automatically during the design modeling phase. When leveraging proprietary synchronous technology in Solid Edge, PMI information is not only used to enhance or simply label the 3D model, but to create and drive it as well. This enables designers to actually create the model more in line with how the part will be manufactured versus traditional history-based approaches. As a result, this saves a significant amount of time, precluding the need to create additional PMI documentation. Let's take a look at this in action. In this demonstration, we're going to walk through a few steps a design engineer may go through to leverage synchronous technology to capture critical product information. We're going to use a design approach called top-down design, where we will design the upper yoke for the front forks in the context of the motorcycle assembly. Designing the parts in the context of other parts guarantees fit and position and avoids interference problems earlier in the design process. Here we include edges for the two front forks. We can also create our own geometry on the fly and choose to have Solid Edge auto-dimension the geometry we create. Now that we've referenced the critical geometry on existing parts within the assembly, we can turn off their display and focus on the design task at hand. Solid Edge supports a full complement of drawing commands. The heads-up display also makes it easy for us to see where we are relative to other geometry upon creation, as well as other critical feedback. In this example, we can quickly complete the main shape of the part by using a common sketching tool to mirror geometry and finish up with a few 2D dimensions. Solid Edge has a unique Smart Dimension command, which will allow us to use one command to create different types of dimensions. In this case, we are using the same Smart Dimension to create diameter dimensions as well as distance between dimensions by just clicking on geometry and dragging to create the dimension that we want. As you would expect, modifying any dimension modifies the geometry. Synchronous technology takes advantage of the closed areas of the sketch and creates regions that we can use to drag and create a 3D part. Transforming the sketch to 3D is a matter of dragging the handle. An important part of this process is that 2D sketch dimensions are automatically transferred to the 3D model and become manufacturing dimensions the shop floor most cares about. In the Pathfinder on the left-hand side of the screen is a node that captures all of the PMI information from the design. In addition, notice that PMI has adaptive view, meaning regardless of the orientation of the model on screen, the PMI information is always readable. As we change a PMI dimension, notice Solid Edge intelligently maintains the symmetry within the model and modifies the corresponding hole on the other side. As we turn off the PMI, we're going to sketch directly on the face of the part. Here, from just two simple lines, we can raise the center section of the part. Again, notice how Solid Edge automatically adds the PMI dimension to reference the height of the part. Next, we will easily copy the top edges down to the bottom face of the model, where this time we will remove material to avoid interfering with other components on the motorcycle. Most 3D CAD systems require you to carefully plan the design steps so that edits can be made later. Using synchronous technology, we can create geometry in the most convenient manner, but have total flexibility in altering the intent later. 3D driving dimensions can be added at any time to simply edit or lock a design feature into shape. Again, notice the PMI drives the model and gives the designer the flexibility to specify exactly how the change will be made, something sketch dimensions don't allow for. The benefit here is that you have flexible designs without having to plan for them. Next, we will add a series of rounds to the part edges. You can choose edges by single click or let the system automatically grab multiple edges. The steering wheel is a unique editing tool that allows us to move, rotate, and align 3D geometry. With synchronous technology, we can rotate and move geometry while keeping the design intent. As you can see, leveraging synchronous technology allows us to speed up the process of design creativity while making sure our designs are model-based definition ready from the start. As we just saw, synchronous technology has many benefits, including being ready for model-based definition. However, not everyone has adopted this method of design and design modification. That's okay. Solid Edge, since its inception, and even today, supports history-based modeling. This method of design utilizes an approach where much of the intelligence, including the dimensional information, is encompassed in underlying 2D sketches. While this design approach isn't as direct as synchronous technology, Solid Edge provides a way for us to easily transfer the 2D sketch intelligence easily into 3D PMI information. Let's take a look. In our motorcycle assembly is a component that was designed using this history-based approach. We'll open it to take a closer look at its detail. One of the caveats to making design changes to history or ordered-based models is understanding how it was designed in the first place. One tool that Solid Edge has for this is the Playback feature, which allows someone to see the steps taken to complete the design and watch the ordered features recompute one at a time. The timing of the playback can always be adjusted, which can be helpful for more detailed parts. When it comes to seeing the actual detail, we can pull up a feature's entire definition, including the 2D sketch and its associated dimensions. In this example, we're selecting the first feature, Protrusion 1, and editing its definition. Here you can see the 2D sketch, its dimensions, and other features to make modifications. This can be repeated for any of the defined features. Since ordered models do not use 3D PMI to create and drive the model, we could manually add this information using the tools found in our PMI toolbox. However, to save time, we can also utilize the information that has already been input into the model and copy that automatically to 3D PMI. In this example, we want to copy specific dimensions from our first feature. Simply select the desired dimensions and Solid Edge will copy those for use in model-based definition. Just as we saw earlier, those are captured in the Pathfinder for display at any time. As opposed to manually selecting individual dimensions, we could also window select all of them to speed up the process. Just as in synchronous technology, the copied PMI has adaptive view and is always readable on screen. Next, we'll determine which ones are critical to keep and select from the list which ones we can easily delete. Adjusting the PMI to be displayed in a neater, more readable fashion is also a very easy thing to do. What about data that wasn't authored natively within Solid Edge? Many companies either receive 2D or 3D data from outside their organization or have legacy data that was created in another CAD software. The data migration tools in Solid Edge allow for users to migrate both 3D models and their corresponding 2D drawings from several different CAD systems and still maintain the connectivity between the two. This in and of itself is a fantastic benefit for companies who choose to continue with traditional engineering and manufacturing documentation. For those companies who want to instill model-based definition, Solid Edge also provides a way to connect the manufacturing information from the 2D drawing directly to the 3D model, which automates the 3D PMI process. Let's check out how to use data from other CAD software to quickly expedite the use of model-based definition. In this demonstration, we're going to take the manufacturing information from a 2D drawing and automate the process of connecting it to its corresponding 3D model as 3D PMI. You'll notice in the standard file open menu for Solid Edge the many different file types we can read in from other CAD software. First, we'll open the 2D drawing, which contains all of the manufacturing detail. One thing to take note of is the scale of the drawing. This will be important when making the connection to the 3D model later. Many 2D drawing applications utilize a layer structure that allows for the user to more easily display the information they want shown. Solid Edge can recognize these layers and replicate the ability to show or hide specific information on the drawing. With a single mouse click, we will activate a handy tool that allows us to either create a 3D model from scratch using the information on the drawing, or, in this case, connect it to our already existing 3D model that we directly opened from the alternative CAD software. Options for projection angle and which dimensions to include are also available. As we select the desired information, Solid Edge will automatically copy and paste the selected information into the associated 3D model. As we rotate the model to several common views, notice how the drawing views and dimensions are automatically aligned. Again, with a single mouse click, the 2D dimensions that were copied from the drawing automatically attach and connect themselves to their corresponding 3D geometry. We now have a complete parametric 3D model that can be driven with PMI. This ability to bring in data that was not authored in Solid Edge and make it intelligent without having to do tedious, history-based feature recognition is a huge benefit and allows Solid Edge users to use data from any source and be ready quickly for model-based definition. So far in our discussion of capturing PMI, our focus has been on capturing dimensional information. However, we know model-based definition is more than just dimensions. It also includes other factors in geometric dimensioning and tolerancing, as well as callouts and other design information. One thing to note about imported data is that it doesn't come into Solid Edge automatically with intelligent features. This can be seen in the Pathfinder. If certain information, such as hole callouts, need to be displayed for model-based definition and be accurate, this information needs to reside in the 3D model. Notice here how Solid Edge has the ability to recognize various features in imported data, including holes. As we activate this option, Solid Edge recognizes the type and parameters of every hole in the model. Now in our Pathfinder, we have actual features that can be referenced at any time and easily edited if necessary. The next step is to graphically call out the holes. This callout associatively maintains the hole feature even as modifications to the hole parameters are made. Here we'll make a quick adjustment to the diameter and depth parameters and watch as the callout automatically updates. Other features such as chamfers and various types of patterns can also be recognized. Again, you'll notice intelligent features are added to the Pathfinder. Notice how as we add a dimension to the shaft feature and make a modification, the chamfer comes along for the ride. As we mentioned at the start of this demonstration, model-based definition also includes other types of information. First, let's quickly display a section view. Solid Edge supports the ability to place model-based definition information in different display states. Various types of annotations can be placed in addition to what's been seen so far. In the feature control frame, we can add various symbols to define material conditions and tolerancing information. After something has been defined once, it can be saved for reuse later. Here, we'll place a couple of feature control frames and a datum on the section view of the 3D model. These are placed easily with a simple click on the edge or face of the intended target. Let's show a more detailed model-based definition with various dimensions, annotations, and callouts. Another nice benefit is seeing the cross-reference to the geometry highlighting whenever an item with model-based definition is selected on screen. Now that we've shown how we can capture PMI dimensions and other annotations, how can we break this information down into bite-sized, more easily readable chunks that can be understood and digested more easily? Model views can be thought of as advanced display configurations. Not only do model views specify which parts are visible, they also control the view orientation and which PMI dimensions and annotations are shown at any time. Various model views can be captured and stored in the Pathfinder, allowing for common tasks such as design reviews to be easily executed. In this next demonstration, we'll show an example of creating a model view showing various PMI information on an assembly and how we can toggle the display of several model views to review different states of our design process. Over in the Pathfinder, you can see the model views that have been created so far. Simply clicking on the view gives us access to apply it to see which information is contained within. Notice with each applied view, the information and orientation dynamically update. Also available is a review mode, which gives single-click access to toggle between each view. Let's start with a blank slate and walk through the steps to show how easy it is to complete the process. First, let's only show the components within the stationary block assembly that we want to focus on. Next, we'll orient the model that will allow us to convey the information in an easily readable display. We'll place a few PMI dimensions, locating a few holes followed by some other critical dimensions on the main block. The same tools and workflows a Solid Edge user would use in the 2D drafting environment are the same tools used here to place PMI. With this being an assembly, we might also want to show an overall height dimension by placing a dimension between two different parts. Instead of showing this on the front side, we can easily push this back to a location that makes more sense. We also have the ability to leverage property information by extracting part names or any other information specific to any part within the assembly. Other information like weld callouts can also be intelligently extracted. With some final adjustments to fine-tune the model orientation and final display, the last step is to create the view. We simply click on the View command, give it a unique name, and specify our desired settings. Now we have access to it along with all the other model views. We've gone through all the steps in Solid Edge to digitally alter the definition of parts and assemblies using our 3D models. How do we now convey this information from engineering to manufacturing or from manufacturer to supplier without requiring them to use the same CAD software? This is where Solid Edge MBD comes in. Solid Edge MBD is a set of tools that allows us to take the information we've created within our model views and publish that content to widely accessible and widely used formats such as 3D PDF and HTML. In addition to conveying the Solid Edge data, other user-defined attachments such as Word, Excel, and PDF, among others, can be added to create a technical data package. One of the tools that makes sharing this information possible is the Solid Edge MBD template editor. This template editor uses the familiar Solid Edge drafting interface to define a configurable template layout. Templates can contain interactive views of the 3D model, a view carousel for ease of transition to model views, bill of material tables, and other customer-specific information. Once the templates are ready for use, publishing the content to 3D PDF or HTML is a breeze. Options when publishing include adding attachments and generating neutral JT and/or step AP242 files, which have the ability to contain the PMI information and be read into various other CAD software and other applications. This allows for manufacturers to send data to downstream suppliers without sending entire proprietary CAD files or forcing suppliers to maintain matching CAD software to read files. If security is critical, a password protection protocol can be enabled, ensuring only those who are intended to consume the data have the ability to open the files. Within the Solid Edge interface inside the PMI tab, you'll notice both the template editor and the publishing tool. Selecting the template editor will take us into the familiar Solid Edge drafting environment. All of the familiar drawing and sheet setup tools are available for easy template creation. Oftentimes, companies want non-editable, inaccessible items placed on a background sheet. This option is available here as well. The first thing we will place on our template is a company logo or image. Just as in a standard drawing template, these images can be easily inserted and sized to fit the desired area. As we decide how to format the template with both viewing areas and other relevant information, you'll notice the added tools Solid Edge MBD offers. We'll start by adding the 3D view, which allows for direct interaction of the model views. A simple drag of the view allows us to size appropriately for our template. The view carousel, BOM table, and fields for user-defined PDF text can be placed and adjusted just as easily. For purposes of time, let's open a more detailed template that contains additional information. You'll notice options can be created for both assembly as well as part-specific templates. In this specific template, we have multiple pages which also contain links to property information. As models get published, their property information, such as part numbers, materials, surface finish, etc., can automatically be extracted to the 3D PDF. Like the template editor, the publishing tool is available from within the Solid Edge interface. Simply specify a name and location to save the document and finish by selecting any of the available options. In our example, we will attach a Word document along with a PDF to include within the data package. From there, select the Publish option and your 3D PDF is on its way. As we navigate the published 3D PDF, a single click on a labeled model view within the carousel makes available all of the information contained therein. Notice consumers can still rotate, pan, and zoom within the window interactively. Also notice a part selected within the BOM table automatically highlights within the view. Here we're transitioning over to the HTML version. As with the 3D PDF, this document is fully interactive. Other options include dynamic sectioning and interactive exploded views. I hope today we were able to convey the many benefits of adopting model-based definition, from enhancing and shortening the design cycle by capturing process information during the design phase rather than after, to reducing costs and rework, and increasing productivity and quality by documenting the information once in a single source, the 3D model, and having the ability to reuse it everywhere else, both within and outside the organization. Okay, we're going to go ahead and open this up for Q&A. I know we're just a few minutes past the 30-minute mark, so we'll try to answer a couple of these questions here within the next couple of minutes. If you do submit a question and we don't have time to get to that today, we will respond back to you. So the first question that came in, which of the items shown today are included with a base package of Solid Edge and which ones are add-ons? So essentially, all of the authoring tools that we showed today to create PMI and model views all come standard with Solid Edge. It's base functionality. So that includes when you design in synchronous technology, that essentially does the PMI automatically for you during that design. We talked about copying sketch dimensions to PMI. That's if you're using history-based, that's an option to speed that process up. And then just creating model views themselves. All of that is standard functionality. Solid Edge MBD, that's a product that contains the last two items we showed in the demonstrations for the template editor and the publishing tool. So that particular product gives additional benefits, and it's relatively inexpensive. So if you're interested in pricing, we can talk to you offline about that one. Second question that's in, are there ways to create 3D PDF without having Solid Edge MBD? That's a great question. Also, the answer to that is yes. So in the standard file save as, there is an option to save out as 3D PDF. And in actuality, if you have your PMI displayed at the time you do the save, the 3D PDF will also capture that information and save it out as well. And that particular option has worked really well for a lot of our customers, and it's a great benefit. So, just to reiterate, where Solid Edge MBD adds value above that is again in the ability to create those custom templates and then save out all of the model views and have those all formatted in a nice, neat package, which is something the standard save as does not do. I guess some of the other benefits of the Solid Edge MBD would be being able to add attachments for your technical data package. And then it also generates other documentation like HTML. And then you can generate JT and Step 242 files. And those types of files also include the PMI information from Solid Edge. So again, I know we're a little bit short on time today. I wanted to answer a couple of questions. Again, continue to submit any questions you might have, and we'll get back to you on that. But again, I wanted to thank everyone for your attendance today. Hopefully, you learned a lot about Solid Edge model-based definition. And once again, thanks for your time.